All right, so today's class is all about colligative properties. So we are dealing with solutions and what happens to the properties of our solution. How does that differ from the properties of our pure solvent? So we're going to look at two different cases with some pure water and then a solution where water is our solvent. So this is our pure water sample. If you remember, water is polar. It's got regions of partial charge, and that makes our water molecules kind of sticky for each other. So if that's the case, our particulate diagram, our diagram showing the particles and how they interact, has this nice perfect order in it. And in this nice perfect world, water will boil at 100 degrees Celsius and it will freeze at 0 degrees Celsius. So think about these temperatures as the amount of energy required to break the temporary stickiness of these water molecules to each other, right? So it's going to take 100 degrees Celsius of energy, right? We've got to have energy to get to that temperature. That is going to make these bonds break and our water go from liquid into gas. The same with freezing. If this was a solid block of ice, we've got to add enough energy to measure 0 degrees Celsius for these the bonds that are holding these water molecules together to kind of become fluid so our water can move around and flow like a liquid. Okay, this is a perfect world with this nice perfect order because there's nothing else in there that's going to jam up this perfect organization, if you will, right? So think about this as like a perfectly organized library. Now, when it comes tricky is when we have extra things dissolved in that pure water. And you can see here, I've shown this as a solution with some ions in here. So if you remember, our ionic substances will break apart into their positives and negatives. This is because water is polar and it has its tiny regions of partial charge. But with these ions, remember, they're actual physical separate things. They only stick together and make a compound because their charges make them attract. When we put them in water, we can kind of break them apart and they become their own individual ions. And they separate and our water molecules kind of budge in and move around and kind of surround each of these ions. Right? So this would be a simple ion that's got 1-to-1, and we look, there's 2 positives and 2 negatives, so that's a 1-to-1 ratio. So this would be something like sodium chloride, NaCl, anything that just has 1 positive and 1 negative. Our ions are in a 1-to-1 ratio. But you can see how this is not as ordered and organized as this one, right? You can kind of think about this pure water as being like OCD, right? It's got this perfect structure, but here, this is more like your room, your messy room, right? So because of this mess here, that influences the amount of energy required to break these bonds. Because remember, this ionic attractions are really strong. Think way back to when we looked at properties of ionic and covalent substances. All of our ionic substances had really high melting points. That means it takes a lot of energy to rip those ions apart. The same here. That's why we'll actually see when we have a solution here, it actually takes more energy than our pure water to boil this. That's because these ionic attractions are very strong. It takes more energy to pull them apart. They're more sticky for each other in our solution than they are in our pure water. And the same with our freezing point. They want to move around and bounce around. This is a very dynamic process. This water molecule has rights to this positive charge, so does this one. So there's this movement that's happening here that means that these things like to flow. They like to move past each other. So it's going to take less energy for them to become a liquid. That's why our freezing points of solutions are actually lower than our freezing point of pure water. So when we're looking at this practically, we're going to see and be able to kind of calculate within our solutions, if we know how many ions we have in there, we're going to see just how much our boiling point is going to be elevated and just how depressed, if you will, or lowered our freezing point of these solutions are going to be. And that's what we're going to be practicing in class today. All right, so here's what you're going to be working with today. I've got this nice little sheet for you. There are a couple of things. With our freezing point depression, this worksheet left off the negative I because our freezing point is going to be lowered. So our change in temperature is going to be negative. So you'll see this in your book with a negative sign in front of the I. In case you forget, you might want to make a little note about that on here, right? So we want to go through and look at what all parts of these equations really mean. This sheet has a lot of great information on there for you, but I'm going to take a time to kind of explain it in a different way just to kind of help you guys understand. So this delta here, anytime you see it, it means a change in. So we are looking for a change in temperature, or how much our new temperature, our boiling point of this solution is going to deviate from what we know to be true about pure water. So remember, pure water boils at 100 degrees Celsius. So we're looking for a change in that temperature, and our boiling point is going to be elevated. So this is going to be a positive number, right? Now we've got this weird variable here for I, KB, and M, right? So we want to look at what each of these mean and kind of understand where we find them in our problem. So M does not stand for moles. It stands for this new measure that we're going to learn about called molality. You don't need to be scared of this. We already know how to figure out all the pieces. So molality is not molarity, right? Molality is our moles of solute compared to the mass of our solvent, right? And most of the time you'll be given this in grams, so you'll have to convert it to kilograms. But moles should be easy for you to figure out if you're given a mass of your substance, right? So we know how to go from 95 grams of sodium chloride into moles of sodium chloride. We can do that in our sleep by now, hopefully, right? We use our periodic table and calculate the weight and do that calculation pretty quickly. So molality is not a complicated calculation for you, right? It's just another one that we have to put in our toolbox and kind of keep track of, right? So the hardest part here is making sure you've got the right units when you calculate the molality. It's got to be moles per kilogram of our solvent. Okay, so that's M. KB is actually a constant, right? So KB is our, it's a factor, and every solvent has its own unique KB. Either the problem will tell it to you, or if it's water, you're going to be expected to know it. So our KB for water down here is 0.52. So don't lose that piece of information, because you might be doing some of these problems and think, hey, I don't have enough information to solve this. Don't forget that we know KB. It's a tool in our toolbox that we can pull out and use. It's not an unknown that we have to calculate, right? Okay, that leaves us with this I. So I is what we call an ionization factor. So I is a whole number. It's a unitless number. It just tells us how messed up our solution is, right? So remember, the more disordered this is, the more effect that's going to have on our boiling point and our freezing point. That's why if we have more ions, we're going to see this change in our temperature is going to be even greater, right? So for things that are nonpolar, are things that do not ionize. I think your worksheet calls them non-ionizing compounds, right? That means they don't break apart into individual ions. That means they stay as one thing. So its factor is only 1. When it messes up this perfect order of our water, there's only one ion in there or it's not even an ion. There's only one thing in there that's messing up this order. So it ends up being pretty darn close to perfect water, right? Now that's different when we have ionic compounds. So we have polar things, or we have ionic compounds, right? So like take sodium chloride, for instance. It's a 1-to-1 ratio. So when it breaks apart, we've got 1 sodium and 1 chlorine. So that's 2 ions. Its ionization factor is going to be twice what something that doesn't break apart is going to be. So it's going to essentially double the change in our boiling point and our freezing point. this change gets even more magnified if we have a more complex ion like MgCl2, which really has 3 ions in it. So when we break it apart, we've got 1 Mg and we've got 2 chlorine ions here for a total of 1, 2, and 3. So the I for this compound would be 3. It would have the greatest impact because it's got the most stuff in there that is going to affect this relationship, this particulate interaction between our actual individual atoms and molecules when they're in this solution. So hopefully that helps you understand all of the pieces, and for the rest of class I'd like for you to look at the examples here and work some of the problems. And if you will take some time to do that, I do have at the end of the video where I work problem number 1 for you. So just pause the video and spend some time trying on your own, and then before class is over, you guys watch and see if you got the first one right. So hopefully you've had some time to kind of work through this and struggle with it on your own. So we're going to kind of come together and do number 1, and hopefully you got it right. So we've got 144 grams of sugar. Now remember, this is sugar, C6H12O6, in 100 grams of water. So we want to calculate the molality, the boiling point of this new solution, and the freezing point of this new solution. So where do we even start? We're going to start with what we know to be true, and we can easily calculate our molality because we're given the gram of this and the gram of that, and we'll remember that molality is moles per kilogram, moles of solute versus kilograms of solvent. So we can find that quite easily. So we're looking over here. We've got our 144 grams. That's of our sugar. Where did I get this number from, though? Where did I just pull it from the air? Hopefully you see that this is the molar mass of sugar. So I got this number by pulling out my handy dandy periodic table and adding the weight of 6 carbon, 12 hydrogen, and 6 oxygen. We add that together, we should get 180. So this is a simple calculation. This is nothing new that you haven't already done a million times, right? We're going from grams to moles. And if we do that correctly, we get 0.8 moles of sugar. So we've got our 0.8 moles, and where did I get this 1 kilogram from? Hopefully you see that that is our mass of water, but instead of grams, I just moved my decimal point over 3 places, and I got that it was 1 kilogram. So to get our molality, we divide 0.8 moles by 1. That just gives us 0.8. So this is our molality and the M that we're going to use for both of these 2 additional calculations that we were asked to make. So that's step 1. Step number 2 is we're going to do our boiling point first. So we know our equation right here. Our change in boiling point is our ionization factor times our Kb times our molality. So we can figure out each of these pretty easy. So if we look at here, our ionization factor, we're told in the problem this is non-ionizing, so that means that it doesn't break apart. So it's all going to stay as 1 unit, 1 particle. So our ionization factor here is just 1. Our Kb is a constant, and since our solvent is water in this instance, we're going to use 0.52. We didn't pull this number out of thin air. We know that this is a constant. It's in our toolbox, and we're going to remember it and pull it out. And M is our molality, which we just calculated. So this becomes a quite easy, a plug and chug problem. So our delta TB, so our change in boiling point, is going to be 1, which is our I, times our Kb, which was 0.52, times our molality, which is 0.8. And if we do that, we get our change in boiling point is going to be 0.416 degrees Celsius. This is a very tiny change. If we were paying attention to significant digits, this factor wouldn't even be enough to make our boiling point of water change any, right? So, but what this means, since this is a positive number, that means our boiling point was elevated. So we've got to take our normal boiling point of water and add this extra to it, this extra energy it's going to take to pull those ions apart from the water that they're interacting with. So our final boiling point for this solution is going to be 100.42 degrees Celsius. Give yourself a pat on the back if you got that right. And let's look now at our next one, which is our freezing point. So this works exactly the same. We're dealing with the same substance, so our ionization factor is going to be 1. Since we're doing the freezing point of this, though, we use our Kf for freezing, our freezing factor, and that's 1.86. This is a constant. It's not something we just pulled from thin air, right? Something it's to be available for us to use. And our molality hasn't changed since we're dealing with the same substance. So it's that 0.8 that we calculated earlier. So, but remember, our freezing point, though, is going to be depressed. It's going to go down. So we've got to include this negative sign here so that we know at the end our temperature is decreasing, right? Because it's going to take less energy to... less energy has to leave for those things to become frozen, right? So 1.86 times 0.8, remember these are just our numbers we're plugging in, and we get that our freezing point is going to be depressed 1.49 degrees Celsius. So this negative sign here means our temperature is going to decrease by 1.49 degrees. These things require less energy has to be subtracted from them. They want to move around, right? So that's why it goes down. Anyway, so we have negative 1.49 degrees Celsius. That's going to be our final freezing point for this solution. So hopefully you got those right, and you'll be able to do the next ones on your own. So this is homework. I expect it to be turned in next week, and hopefully I will see you guys soon. Thanks.